Today we're going to use our definitions of average acceleration and average velocity. Average velocity is change in position with respect to time. We're going to use those definitions to see if we can develop some equations that allow us to describe the motion of objects. What's going to be required, since this is acceleration, velocity, time, velocity, position, time, we really want to be able to mix these two equations somehow and figure out if we can develop a system of equations that combines both of them. So the first thing we want to do is let's just work with this acceleration equation. Rearranging this, we get change in velocity is average acceleration times change in time. And we know change, delta, always means final minus initial. So change in velocity is going to be v final minus v initial. And that's going to be my average acceleration times t final minus t initial. And then one of the things that we'll do is we will stipulate here that the initial time, t0 equals 0. And that just means we start our stopwatch at the beginning of the problem, and that allows us to just get rid of the subscript, so the final time will just always be listed as time. So in this case, that allows us to just get rid of this initial time and that subscript, so we get v final minus v initial equals average acceleration times time, or v final equals v initial plus t. Alright, so that's a useful equation. It's just, again, did no mixing or anything. We just rearranged, got rid of some deltas so that we know the final velocity in terms of initial velocity. We can do the same thing over here with our average velocity equation. We can say delta x is equal to average times delta time. But again, we know delta time is t final minus t initial, which, based on our definitions, we're just going to say time. So delta x is v bar t. But we also know, if we look over here, we know average velocity. We know how to find the average. You just add them all up and divide by 2. So average velocity is v initial plus v final, and then divide by 2. That is going to be the definition of average velocity. So I'm going to be able to say change in position is average velocity, v initial plus v final over 2, times delta t, which in our notation is going to be time. So we have one equation. We took out our acceleration equation and just rearranged it a little bit. We took out our velocity equation, rearranged it a little bit, and used our definition of average velocity to get things in terms of beginning and end variables. Now what we want to do is we want to be able to mix. So we want to take this equation right here, and we want to do a couple of things with it. We want to mix in this acceleration information, and we can do it one of two ways. We can, in one case, we can use it to eliminate the final velocity. So if we eliminate v final is one way to do it. Another way to do it would be to eliminate time. Okay. And a third way to do it, so we've got final velocity, time. A third way to do it would be to eliminate initial velocity, but it turns out that we don't really need that equation very often, and if we do, it's the same process, so we can develop that later. So how do we eliminate final velocity? Let's just start with that. So we've got our equation. Delta x is v0 plus v final over 2 times time. I know what final velocity is. Okay, I'm going to take this final velocity equation, and I'm just going to plug it in right there. Just substitute it. So I'm going to get v0 plus v0 plus at over 2, all of that times time. So I just did that, and we noticed that my v final is just right here. That's my v final. Right? I just made that substitution. So now we can simplify. I've got v0 and v0, so that's 2 v0s. So I've got 2 v0. I'm going to separate out. Oh, well, let's just do it all. At over 2 times time, multiply times time. So I've got 2v0 t plus a t squared over 2, and then I'm going to separate out those fractions, so it's going to be v0t plus 1/2 a t squared. That's my delta x. Notice that our goal is to eliminate v final. We plugged in the v final, made that substitution. There's no v final in this equation. Okay. What if we want to eliminate time? So we do the same thing. We start with our same equation. Delta x is initial plus final over 2. That's my average velocity times time. But now I need an equation for time. So I'm going to have to take this equation and I'm going to have to rearrange it. I'm going to have to say v final minus v initial over a is equal to time. Right? So I just solved this first equation for time. Now I can take this time equation and plug it in right there. And again, that does the mixing, right? It takes my acceleration equation and plugs it into my position or velocity equation. My acceleration equation plugs it into my velocity equation. So I get v0 plus v final over 2 times time, which is v final minus v0 over average acceleration. Okay? And again, this is the substitution. So I've got the average time, the average time. So what do we end up with? Well, I've got my basic a minus b, a plus b is a squared minus b squared. So I end up with v final squared minus v initial squared. If I FOIL the numerators here, or a plus b, a minus b, so, and that's all over 2a bar, and that's going to be equal to delta x. And I'm going to just rearrange that so it's more conventional. So put the 2a over here, so v final squared minus v initial squared equals 2a delta x. And then move my v0, so v final squared equals v0 squared plus 2a delta x. So there's a third equation, and you notice there's no time. We eliminated time in that variable. Both of these equations have v0 in them. If we did this again, solved this equation for v0, and then pushed it through the same position equation, then we would end up with an equation without v0, but it would have v final and time. And if we need that later on, we will use it. So a couple of comments on these equations. These equations are what we call our kinematic equations. And I want to clean up some notation a little bit. So our kinematic equations, equations that describe the motions of objects. And notice that in each of these equations there's an average acceleration. We're going to go ahead and just say that the average acceleration is the instantaneous acceleration, which implies that the acceleration is constant or not changing. All right, so it could be constant at 10 meters per second squared, it could be constant at 0, but as long as it's not changing, then we can use these equations. If they are changing, if the acceleration is changing, then we go all the way back up here. This is no longer true. The average acceleration is not changing velocity with respect to time if the acceleration is constant. So it is not constant. So we have to require this. Okay. And then just by convention, we'll also, like we did with time up here, we said that the final time we'll label as t. We'll also just say final velocity. We'll get rid of that subscript and we'll say that that's labeled as v. So what we can do then is we can write these equations. We'll have three equations. V equals v0 plus at, right? That's this first equation, just getting rid of the subscript for v final and the a bar. We've got delta x equals v0 t plus 1/2 a t squared, and we've got v squared equals v0 squared plus 2a delta x. And what that means is anytime there's no subscript, then no subscript means that we are going to imply or remember that that is the final value. All right, so these guys right here are what we're going to call our kinematic equations. And we're going to remember that their requirement is that the acceleration is constant, and we're going to remember where do they come from. All they do is they come from our original definitions of acceleration and velocity. So what do we do with these? Let's drive these around the block a little bit. So if we want to, just write these again for you, v equals v0 plus at, delta x equals v0t plus 1/2 at squared, v squared equals v0 squared plus 2a delta x. So let's do a problem. Let's just see if we can describe the motion of something. Let's take a car traveling, let's say 25 meters per second. So you're just driving down the road at 25 meters per second. And let's say you hit your brakes to a stop. Okay, 25 meters per second to a stop. And let's say that the time interval, it takes, say, 5 seconds. Okay, so car's traveling 25 meters, you brake to a stop, time interval is 5 seconds. It turns out, just by convention, if you look through all of these equations, there are 5 variables. And your general process is going to always be to list your 5 variables, v0, v, a, t, delta x, and then decide which ones you know and which ones you don't know based on your problem. So in this case, car traveling 25 meters per second, we will call that our initial velocity. We're starting at 25 meters per second. Brakes to a stop, that's my final velocity, 0 meters per second. Time interval of 5 seconds, that's my final time, so 5 seconds. So we'll notice that I know 3 things. I don't know the acceleration and I don't know the distance, which means I can solve for both of those. Maybe my question is, how far does it travel? Okay. So you'll notice that in all 3 of these equations there's an acceleration. So we're going to have to find the acceleration. Turns out if you know 3, you can find the other 2. So let's find the acceleration. I know initial and final velocity and time. So I'm going to look at that first equation. V equals v0 plus at. I want to solve it for acceleration. So a is equal to v minus v0 over t, which means it's going to be final velocity is 0 minus 25 meters per second over 5 seconds, which means I'm going to get minus 5 meters per second squared as my acceleration. And I'm going to go ahead and plug that in over here, minus 5 meters per second squared. So a quick interpretation, does it make sense that my acceleration is negative? Yes, I'm losing velocity, I'm slowing down, so that definitely makes sense. So now I have to decide I want delta x, and I know that equations 2 and equations 3 both have delta x, so it doesn't matter which one I use. Let's just use them both and see what happens. So if I use equation 2, I'm going to say delta x equals v0t plus 1/2 at squared. So initial velocity is 25 meters per second. Time is equal to 5 seconds plus 1/2 times negative 5 meters per second squared times t squared, which is 5 seconds squared. So 25 times 1, so that's going to be 125 meters. 5 times 5 is 25 times 5 is 125 divided by 2, so it's negative minus 62.5 meters. So we're going to end up with 62.5 meters is the distance the car travels during that time. What happens if we go over here and use equation 3? V squared equals v0 squared plus 2a delta x. So I'm looking for delta x. Delta x is equal to v squared minus v0 squared all over 2a. So final velocity is 0 minus initial velocity is 25 meters per second squared. all over 2 times negative 5 meters per second squared. Okay, so 25 times 25 is, so we're going to end up with minus 625 meters squared per second squared over minus 10 meters per second squared, which means all my units work out, meters squared, second squared. I'm going to end up with plus 62.5 meters. And again, it matches. We notice that the distance is 62.5 meters, so it doesn't matter which equation we used at that point, we just choose which one is most friendly to us algebraically.